Sulfur is the chemical element with atomic number 16, represented by the symbol S. It is an abundant, multivalent nonmetal. At normal conditions, sulfur atoms form cyclic octatomic molecules with the chemical formula S8. Elemental sulfur is a bright yellow crystalline solid. Sulfur can be extracted using the Frasch process, which involves pumping superheated steam and hot compressed air down a series of pipes to melt and collect molten sulfur. Sulfur also exists in various allotropes, including crystalline forms like rhombic and monoclinic sulfur, and amorphous forms such as plastic sulfur. Monoclinic sulfur, or beta sulfur, is the only stable allotrope between 96 degrees Celsius and 119 degrees Celsius. The crystals are long, thin, and needle-shaped. 96 degrees Celsius is the transition temperature where the two major allotropes change form. This diagram illustrates the Frasch process for extracting sulfur. Superheated water is pumped down, melting the sulfur, and compressed air forces the molten sulfur foam to the surface. Comparing physical properties, rhombic sulfur is bright yellow, octahedral, and stable below 96 degrees Celsius. Monoclinic sulfur is amber, needle-shaped, and stable between 96 and 119 degrees Celsius. Amorphous sulfur has no definite crystal shape and is often a pale yellow deposit. Plastic sulfur is a supercooled form of sulfur that is soft and elastic but unstable, eventually reverting to rhombic sulfur. Physical properties of sulfur include being a yellow solid, insoluble in water but soluble in carbon, IV, sulfide, and a poor conductor of heat and electricity. When sulfur vapor is condensed, it forms fine powder called flowers of sulfur. Molten sulfur poured into molds forms roll sulfur. Sulfur has oxidation states ranging from -2 to +6. It directly combines with nearly all metals and most nonmetals. Sulfur reacts with metals to form sulfides when heated without air. It burns with oxygen to form sulfur, IV oxide. Sulfur is used in vulcanization of rubber, as a fungicide, and in manufacturing products like skin ointments, matches, and fireworks. Sulfur, IV oxide, SO2, is produced by volcanoes and industrial processes. Combustion of fuels containing sulfur compounds also generates SO2, which can lead to acid rain. Preparation methods include the action of hot tetraoxosulfate, VI's acid, on copper turnings. Sulfur, IV oxide, is a colorless, poisonous gas with an irritating smell. It is very soluble in water, forming trioxosulfate IV acid, and is about 2.5 times denser than air. Chemically, it acts as an acid, reacting with alkalis to form sulfite salts. Sulfur dioxide is a good reducing agent, used as a bleaching agent for materials like paper and clothes. It can decolorize substances, such as purple acidified potassium permanganate and orange acidified potassium dichromate. A solution of SO2 in water acts as a bleaching agent, dissolving in water to form trioxosulfate, IV acid, which reduces the dye. SO2 also undergoes direct combination reactions and acts as an oxidizing agent in the presence of strong reducing agents like hydrogen sulfide. Sulfur IV oxide is recognized by its irritating smell and confirmed by its bleaching action on moist flowers and its reducing effect on oxidizing agents. Uses include making tetraoxosulfate, VI acid, acting as a germicide, fumigant, and bleaching agent for fabrics like straw and silk. Liquid SO2 is sometimes used as a refrigerant or a preservative. Trioxosulfate, IV acid, H2SO3, is an unstable acid formed when SO2 dissolves in water. It is a dibasic acid. It can be prepared by dissolving SO2, liberated from adding concentrated HCl to sodium trioxosulfate, IV, in water. Trioxosulfate, IV acid, is a colorless, unstable acid that turns blue litmus red and smells of sulfur, IV oxide. Chemical properties include oxidation by air to tetraoxosulfate, VI acid, acting as a reducing and bleaching agent and acting as an acid. It is used for bleaching and as a germicide. Trioxosulfate, IV, can be prepared through neutralization or precipitation. It has properties like limited solubility for metallic forms and reacts with acids to evolve SO2. It also acts as a reducing agent. To test for trioxosulfate, IV, warming an unknown substance with dilute acid indicates its presence by evolving SO2. Alternatively, adding barium nitrate forms a white precipitate that dissolves upon adding dilute nitric acid. Tetraoxosulfate, VI acid, H2SO4, historically known as vitriol, is a strong mineral acid. It has numerous applications in chemical synthesis, fertilizer manufacturing, and lead-acid batteries. Industrially, tetraoxosulfate VI acid is produced using the conventional contact process. Stage 1 involves burning sulfur in air to produce sulfur dioxide. Stage 2 oxidizes the sulfur dioxide to sulfur trioxide using V2O5 as a catalyst at high temperatures. The reaction in Stage 2 is reversible. Stage 3 absorbs the sulfur, VI oxide, into concentrated H2SO4 to form oleum. Stage 4 dilutes the oleum with water to produce concentrated tetraoxosulfate, VI's acid. Directly dissolving SO3 in water is avoided due to the highly exothermic reaction, which produces a corrosive aerosol. Physically, concentrated H2SO4 is a colorless, viscous, corrosive liquid with a density of 1.84 GCm cubed. This flowchart summarizes the contact process for producing sulfuric acid, from cleaning and compressing gases to dissolving sulfur trioxide in concentrated sulfuric acid to form oleum, and finally reacting oleum with water to form sulfuric acid. This diagram illustrates the industrial setup for the contact process, including the SO2 furnace, precipitator, scrubbing and drying towers, heating chamber, and reactor. Concentrated H2SO4 has a strong affinity for water, releasing a large amount of heat upon dissolution. It is also hygroscopic. Chemically, dilute H2SO4 acts as a strong acid, reacting with metals, carbonates, and bases to produce salts.